Namaste and welcome to VD Decode YouTube channel.
Indian summers routinely push past 45 degrees Celsius. If you're looking at buying an electric vehicle, that temperature number probably brings up a specific fear. What happens when the heat destroys the battery, leaving you with a replacement bill for hundreds of thousands of rupees? That fear assumes an EV battery is a single, fragile object that fails all at once. In reality, it operates more like a heavily armored energy vault. Inside the chassis, the battery pack is broken down into smaller, manageable sections called modules, and inside those modules sit the individual energy cells. These high-voltage pathways are surrounded by a dedicated support system. A network of liquid cooling channels regulates the internal temperature, while a computer called the battery management system continuously monitors the voltage and health of every single cell. The physical hardware keeps everything protected from the outside. But the actual performance, durability, and cost of the vehicle are dictated entirely by what sits inside those cells, the specific chemical mixture storing the power. Surviving extreme road conditions relies less on a thick metal shell and entirely on whether the manufacturer chose a microscopic chemical structure built for endurance over raw speed. This data matrix chart compares the dominant battery chemistries on the market today. The first column tracks lithium iron phosphate, or LFP. It is highly stable, with a flash point of 500 degrees Celsius, and it can easily survive over 3,000 charge cycles, giving it a reliable lifespan of a decade or more. The engineering compromise with LFP is its lower energy density. Because it holds less power per kilogram, manufacturers have to build physically heavier packs to achieve high driving ranges. The second column tracks nickel manganese cobalt, or NMC. By blending these specific metals, engineers achieve a much higher energy density. This allows premium vehicles to pack more range into a lighter, smaller space, delivering rapid acceleration and longer highway driving. But that performance comes with a thermal cost. NMC has a much lower flash point of 210 degrees Celsius. To operate safely in hot climates, these batteries require continuous, aggressive liquid cooling systems to prevent overheating and degradation. Researchers are currently testing solid-state batteries, expected to hit the commercial market around 2027. These replace the liquid electrolytes with solid materials, aiming to combine the extreme thermal safety of LFP with the high energy density of NMC. Until then, no single battery chemistry is objectively perfect. You are choosing a specific balance of manufacturing cost, thermal safety, and total driving range based on how you plan to use the vehicle. A climate where summer days regularly cross 40 degrees Celsius accelerates the breakdown of sensitive lithium-ion electrolytes. It is a punishing environment that tests the thermal limits of any chemical mixture. For mass-market models facing daily start and stop traffic and frequent charging under the sun, LFP has emerged as the clear winner. Its natural resistance to thermal runaway provides a massive safety buffer for everyday drivers. The global supply of these highly stable LFP cells is largely driven by CAT, a company that recently developed the Shen-Xing Plus architecture, pushing LFP range capacities past historical limits. Similarly, BYD developed their specialized blade battery, which uses long, structural LFP cells to further increase stability. This is the chemistry powering vehicles like the Atto 3 on Indian roads right now. Meanwhile, companies like Samsung SDI and Panasonic are focused on pushing the boundaries of high-density NMC cells and accelerating the research and development required for future solid-state implementation. When you select an EV in India today, you are picking a side in this global manufacturing debate: extreme thermal stability for daily mass transit or advanced energy density for premium performance. If a battery experiences severe degradation, the out-of-warranty cost for a complete pack replacement looks terrifying. For a premium model with a large battery like the Hyundai Ioniq 5, a completely new pack can cost upwards of 12.5 lakh rupees. But as the schematic shows, you rarely need to replace the entire pack. Because the battery is divided into separate sections, service centers can run a diagnostic, isolate the specific failed module, and swap only that single piece. Instead of paying for a full replacement, a module swap usually costs around 2 lakh rupees, a fraction of the total price. Furthermore, almost every mainstream brand now includes an 8-year or 1.6 lakh kilometer warranty that covers early degradation entirely. By designing the hardware in replaceable sections and backing it with extensive legal warranties, manufacturers have minimized the massive financial risk previously associated with early EV adoption. If you commute strictly within city limits and prioritize long-term durability in high-heat environments, look for a vehicle using an LFP battery. It handles the daily thermal stress with ease. If you regularly drive long highway distances and are willing to pay for fast acceleration, NMC is your target. Just ensure you stick to a 20 to 80% charging routine to keep those sensitive cells healthy. The modern EV is an engineered piece of technology. The maturation of battery chemistries, combined with comprehensive warranties, makes these vehicles highly reliable assets for the long haul. If you found this breakdown useful, 80% of our viewers aren't subscribed. Hit the subscribe button and turn on notifications so you don't miss our next deep dive. Knowing what goes into your vehicle ensures you buy the exact tool for the job. Understanding the chemistry powering your car is the surest way to make a confident financial decision.